Okay, let's get started. Good morning and good afternoon, everyone, depending on where you are. Welcome to our first webinar on the topic of autonomous driving simulation. My name is Yijun Fan. I'm the Automotive Application Manager at MSC Software. Dr. Luca Castignani will be today's presenter. Luca has many years of experience in the automotive engineering space, and before joining MSC, Luca worked as an engineering manager at Ferrari for almost 13 years. At this point, I'm going to pass the presenter to Luca.
Hello, good morning to everyone, or good afternoon, depending on which time zone you are in. And thanks to Yijun for his introduction of myself. As you can read from the title slide, I'm the autonomous strategist at MSC Software, and probably this would require a little bit of explanation what is a strategist, but you will see during the presentation why there is a need for someone that takes care of getting together all the technologies that are involved into the development of self-driving vehicle. So let's get started. The very first thing I want you to focus is about a concept that is pretty common in autonomous driving, the concept of corner cases. Quite often corner cases are referred as something that very seldom happens on the road. But what does it mean, very seldom happens? Is this, for example, a corner case? I mean, this is just a mirror that is crossing a road, a street. Every day, thousands of mirrors are delivered, and many of them cross the road. So is this something that only seldom happens? And what is going to be the reaction of a self-driving vehicle, and in particular of the camera of a self-driving vehicle when seeing the image of the self-driving vehicle itself reflected in the mirror and then approaching almost at the same speed the vehicle itself? This other one looks to be another corner case, right? It's someone dressed up as a dinosaur. Okay, you may choose a different costume on Halloween time, but definitely during Halloween time, especially in the US, having pedestrians that are somehow not recognizable as common pedestrian is not corner at all. Yes, it's corner 364 days of the year, but very common on that very specific day. And the number of examples are literally countless. This is a good example of street art. What is going to do a system that is camera-based and is tricked by this 3D painting on the pavement. And sometimes we have other situation like this is, I think, is brilliant. Is just an advertisement. It's just a way of depicting the seat for a bus stop. But then the perception layer of self-driving vehicle can imagine that this person, presumably on a wheelchair, may be on the verge of crossing the road, and this causes a sudden stop of the vehicle. So I typically have a different take on what is a corner case. The corner case is something that most of the time engineers don't think about. I don't think engineers are the best person, they have the best attitude to imagine this corner case. We as engineers, we tend to believe in straight lines, in rigorousness. We tend to simplify the reality so we can apply our knowledges. But actually, the reality is way richer than our few physical laws. So think twice next time you think a corner case is really a corner. This because if you really imagine that developing a self-driving vehicle means just putting a set of sensors on top of a car, and thanks to our friends of autonomous stuff, this is becoming easier and easier every day. Well, you should remember that, yes, it just takes 20% of the effort to do the 80% of the work. But then, oh, the most of the work is still in front of you. So you probably remember we are all in this business since some year, and we just need to rewind of a couple of years, 2017, plenty of announcements about self-driving vehicle coming today, tomorrow, in 2017, 2020 maximum. There were most of the automotive OEM presenting their plans and moving forward. But then something happened. Every one of you knows about this accident in Arizona. A self-driving test vehicle hit and killed a pedestrian in a nighttime scene where probably a human driver wouldn't be able to do anything better. But there was such a hype on autonomous vehicle that this was just unacceptable for many. And I found this quote on LinkedIn from this guy, and I think it's really relevant. It's unacceptable that to perform a test on a software piece that is not yet complete, is not yet debugged, is not yet ready to go anywhere, we go on the road, we risk the life of all the pedestrians that are innocently involved. They have no clue of what's going on. And if anything goes wrong, like in this case, they risk their lives. In this specific case, I would say that plenty of things went wrong. And one of the things that went wrong, the most technical one, is that the system was not able to decide what was this object that was in front of the vehicle. The vehicle has seen some object 6 seconds before hitting, but then the perception layer was unsecure on what to do, to initiate a braking, an evasive maneuver, or whatever. And when it finally detected, thanks to the headlight, that it was actually a pedestrian partially hidden by a bicycle, it was definitely too late. You can't complain that, well, this was just an accident, and neither you can blame the software engineer that wrote that piece of software. Engineers have the right to do mistakes. What we have to avoid as a society and as development manager is that these sort of errors cannot have this level of consequences. So no surprise that the public started having some concern. Hey guys, are you really sure you're doing everything right? So yeah, the public was pretty hard on Uber especially, but I wouldn't say that the status of art on all the other companies was much better. And even Waymo, that is, I would say, largely renowned to be very sensible to safety, has suffered of attack of people that were worried of seeing these tens, hundreds of vehicles navigating without a person behind the wheel in their neighborhood. So no surprise that at CES this year, of course, there was a lot of rumors about self-driving vehicle, but at some point it was pretty clear that, hey guys, in 2019 we have to adjust our way of operating, and we have to find better way to develop self-driving vehicles. And the biggest takeaway, I think, is summarized by this slide. I think you are all familiar with the 5 levels of safety of the Society of Automotive Engineering in the US. So some years ago, 2013, it was imagined this very nice path from almost no automation, driver assistance, and then partial automation, the famous level 2, up to the full automation. This was somehow encouraging, sort of, yes, at every step you can learn from the previous one. But what if the level 3 does not exist? Why I think so? Well, because level 3 is totally undefined. Some OEMs still advertise about level 3, but most of OEMs and tier 1 are skipping this designation. And the reason is pretty simple. You can't pretend that a human that is sitting on the driver's seat and is reading a newspaper is requested to take control of his vehicle and is able to manage a very complex situation that the system is not able to manage in a matter of seconds. You have to allow at least 30 seconds before human regain the situational awareness, takes control of the steering wheel, the throttle, the brakes, eventually even wake up because maybe he was taking a nap, find out what is going wrong in its surrounding, vehicles on its side, and then take a meaningful action. This is not something you can achieve in few seconds, but actually sensors have a limited range, less than a few hundred meters. So if you divide these few hundred meters by the typical highway speed, it means that you typically cannot give to the human driver the backup more than 3, 4, 5 seconds for reaction, and this is absolutely not enough. So this is clearly pushing for a shift of paradigm. There has to be a contract between the human and the self-driving vehicle. Or the human is driving and the self-driving vehicle is assisting at its own best this task, or the system takes care of every single piece, also including managing never-seen situation of the ride. If we stay in this paradigm, we see there is a clear dichotomy. The simple ladder from pure mechanics to pure electronic is no more established. So how do we get there now that we are conscious that the challenge is really higher? Well, an example is the one of Waymo. They are directly pushing for level 4 self-driving vehicle, and to do that they are fully leveraging simulation. Yes, they are mostly renowned for all the road testing they are doing, and in fact they have scored more than 16 million kilometers in these 9 years, and they have tested in a lot of different environments in the US. Okay, they started in California, but then they propagated to Arizona and even in less favorable weather condition. But what is not really known is that Waymo has set up a simulation environment that every day allows them to run more than 10 million miles with 25,000 of vehicles in parallel. This is the way in which they can test, adjust, simulate, optimize, and only once they have confidence that the driving algorithm has reached a safe enough step, they move to the real world. So it's clear that if we want to achieve real self-driving, we will need to go one day or the other on the road. But going on the road is very dangerous and slow. So we should benefit all the other development opportunities. And from this perspective, simulation is the one that has the best advantage. I will not be repeating the same mantra that simulation is repeating over and over the time. That is, well, you may cut the cost, well, you may speed up the development process and all this good stuff. In the case of self-driving vehicle, we have even more compelling reasons to do this. And one of these reasons is exactly the repeatability. You never face exactly the same situation 2 times when you go on the road. So the same position of the pedestrian, the same clothes of the pedestrian, the same speed of all the vehicles around you, the same time of the day. So you don't know exactly if your algorithm has been really improved. And the other thing is that when you go on the road, and even if you collect millions of miles of data, well, all this data, they don't have the ground truth embedded. So you need to undergo a process of labeling that is really tedious and time consuming. On the other hand, the ground truth, where you can directly compare the algorithm perception with the reality, is fully available at simulation level. There are other advantages, of course, for doing simulation, but we will touch them during the rest of the presentation. So let's give a look to what is the simulation workflow in the context of self-driving vehicles. So we definitely need a coordination process because actually autonomous vehicles are very different from the rest of the typical engineering workflow in the sense that to develop a self-driving vehicle, the amount of effort that you spend modeling the system you're interested in, your vehicle, is just a minority with the effort that you need to spend to model the environment in which this vehicle operates. So I take almost for granted that you have a vehicle model of your car, your truck, your bus, and this is the mechanical representation of the system. But then you need to build a road network and you possibly want to add a 3D environment like buildings, because buildings, they cast shadow. You want to model tunnels because in tunnels maybe your GPS signal will be weaker or absent at all. And then you need to add other participant vehicles, typically bikers, motorbikes, buses. Last but not least, weather conditions, they can affect quite a lot sensors, and rain, fog can very easily impair LiDAR and cameras. On the other hand, humidity has some consequences on ultrasonic devices and so on. And finally, pedestrian and animals. They are typically classified by the Euro NCAP as vulnerable road users. So there are specific tests that, according to the Euro NCAP, the vehicle needs to pass to be properly rated. Once you have all these ingredients in your recipe, well, the system will compute for you what your sensors will perceive of the scene. Of course, will provide you also the ground truth, but most meaningfully will create what your LiDAR, what your radar, what your cameras are seeing. And with this information, you can perform the typical steps of the self-driving workflow. So the sensor fusion, the object detection, the prediction of the movement of the other actors, and then the path planning of your own vehicle, and finally the actuation that closes the loop. In this view of the world, it's pretty clear that the green boxes is what our customers typically develop. We at MSC, we prize ourselves to enable you to do this, providing a comprehensive solution for the simulation side of the story. Not always, anyway, a full simulation workflow is needed. Sometimes, specifically for the perception phase, you can even leverage a very simplified vehicle model. You don't need that much about tire properties, not that much about damping, hysteresis, and so on. And then you basically need to generate tons and tons of images that then can be leveraged to train your sensor perception. So your AI for object detection, for proper clusterization, for determining the position of every actor. And this workflow typically runs at a speed that is close to real time, basically because you need the best accuracy in reproducing the sensor and interaction of the sensor with the environment. Another specialized workflow is the one that is typically referred as the path planning workflow. The path planning workflow as a prerequisite that the vehicle has gained, maybe with some level of uncertainty, a clear understanding of its surrounding. So the sensor has already built the so-called object list. Which other actors are on the road, where are they positioned, what is their velocity, their heading, and so on. This is typically done with the purpose of training the safest path planning, the safest path forward for the vehicle, avoiding as much as possible any crash with any other participant. And this exactly because we don't need to simulate the full rendering of the scene, typically runs much faster than real time. In this case, you need a very good vehicle model because especially for evasive maneuvers, the tire friction, so the stability of the vehicle can be really at risk. So let me introduce Biggity. VTD stands for Virtual Test Drive, and is an environment that allows you to do exactly what we have just described. You can design 3D environments, you can design roads, you can populate this environment with trees, houses, buildings, and many other props. Of course, you can inject all the traffic that you want according to predefined models, like the Sumo model is an open source model from the DLR, so a German model, or maybe supplied by a third party, like we are going to be very soon integrated with PTV Vissim. Of course, you can add other actors, like pedestrians, like animals. Plenty of animals are already modeled, even kangaroos, if you're interested. And of course, you can change in real time, in a scripted way or in an interactive way, the weather conditions. So is it rainy, is it sunny, cloudy, foggy, or whatever. All of this is then computed in real time, in this case, having in mind the surface roughness, so we are not just showing texture. The road here is a really rough road, so there is roughness, there is difference in the elevation of the road, and then puddles accumulates where the road is lower, and so on. The same simulation environment, depending on the task of the developers, can be deployed on a personal computer, and this is typically the case for modeling the loop. So maybe you are an ADAS developer and you want to double check if the next ACC module is doing its job. That's the typical application on a personal computer, or maybe in an integrated environment. For example, for software in the loop testing, in which you are responsible just for a fraction of the complete software stack, and you need to double check that your fraction is behaving correctly with the continuous integration process. The same can be applied to the test bench. Hardware in the loop testing is pretty common in this field. This testing can involve actuators like steering columns, or maybe involving a sensor like real cameras. The same environment, again, can be used in driving simulators. In this case, you can simulate how the advanced driving assist system is interacting with the driver, if the warnings are correctly perceived by the driver, or if something is judged unsafe as a maneuver by the driver, and so the driver has the tendency of taking over the system because it feels unsafe. And of course, we are moving into HPC, and pretty soon even on the cloud. HPC is fundamental, because we just said that we need to run millions and millions of miles of simulation, and of course you can't do that on your personal laptop. Let's go and check what is the current status of simulation adoption into this workflow. At MSC, and especially thanks to the fact that MSC belongs to the Hexagon family, we have the chance to connect so many disciplines together. So we were just mentioning that you need a proper vehicle model, and in this case it's represented by the ADAMS. ADAMS is the typical environment where engineers set up the driving attributes of a vehicle. You can design suspension, you can design the driveline, you can assess durability, MVH, comfort, and so on. But sometimes you don't need this level of detail, so you can easily transform the vehicle model from ADAMS into an ADAMS real-time model that then, of course, can be injected into VTD, that, by the way, is vehicle agnostic, so can use vehicle models coming from different sources. And then VTD will combine this vehicle model with the AI driver, with the traffic, with the sensors, and the 3D environment, so that the simulation workflow can be completed end-to-end. Another part of the story we are working at MSC is the data management, and then closing the simulation loop. Because if you are generating millions of miles at every iteration, it's virtually impossible for an engineer to give a look to single results. So you need a way to to have proper data analytics, to have KPI and dashboarding, and possibly to have some smart sampling technique, some AI-assisted workflow that lets you dig into the cases in which the vehicle isn't really behaving as expected. And this, of course, is depicting the simulation side of the story. But then at Hexagon, we have the chances to bridge the gap and bring reality into the simulation world. So let me give you a couple of examples. Novatel. Novatel is a company belonging to Hexagon, and specifically to the branch Positioning Intelligence. And Novatel, they provide very accurate positioning for autonomous system. Now, we all know that the GPS precision is the same for everyone, and is few meters of accuracy. So if you want to achieve a better accuracy in the range of centimeters, you need to apply correction techniques to this GPS signal. Exactly, this is what Novatel does, applying all these correction techniques. And it makes sense you want to apply these correction techniques also on simulated signal to evaluate, for example, characteristics like the time to fix of the vehicle after the vehicle gets out a tunnel. Autonomous Stuff is a very well-renowned player in the autonomous world. They have more than 2,000 customers all around the world, and they develop for their customer self-driving test platform. And this can include the vehicle itself with several models already available, can include a full range of sensors from cameras to LiDARs to infrared camera, GPS system, IMU, and so on. On the other end, to Hexagon, we also have the chances to directly connect with the Geosystem branch, and in particular in this case we find the Leica team. The Leica team has a very nice piece of hardware and software, is the Leica Pegasus. As you can see, it can be very conveniently mounted on top of a vehicle, and then driving at regular speed. You don't need to close the road to perform the scanning. You can measure with the LiDAR and cameras the road. This information can then be almost completely automatically post-processed, and then the road network is reproduced in the digital environment. The other initiative we are working on is leveraging the content program of Hexagon, where the whole US territory and the whole Europe has been manned from aerial with cameras and LiDAR, with a resolution varying from 30 centimeters for country zones to down to 5 centimeters in cities with more than 1 million inhabitants. So, given this richness, which are the bottlenecks? Why simulation is perceived sometimes as not the way to go forward? Well, I think there is, first of all, the question that I receive the most is, how accurate are your sensors? And this to me is a very important question, because the sensor, the most important thing a sensor model needs to be able to deliver is not the accuracy, but how it resembles reality. And the real sensors are not accurate 100%. So you need to be able to reproduce this inaccuracy of the sensor. You need to reproduce how the sensor will interact, for example, with the raindrops. So the LiDAR beam will be scattered and you will not receive that information back. So that's definitely one of the top points. The other point is about building these 3D environments. If you need to simulate millions of miles and you want to test in diversity, you can't simply run and rerun the same 100 kilometers. You need to have different environments for highways, for urbans. You need to have super elevated roads. You need to have tunnels. You need to have small villages and crowded cities and so on. But if you build manually these environments, is it really taking forever? Last but not least, if you're simulating really millions of kilometers, you are generating petabytes of data on a daily basis. So how do you get the best out of all this data? It's true, data is the new oil, but the oil needs to be refined before being injected into your car tank. So let's give a look. Well, as I told you, the ideal sensor does not exist in my opinion. It really depends on the task that you have to tackle, and that's the reason why with BTD we have different levels of accuracy and speed provided for the same sensor. So you may want to simulate a LiDAR, for example, as a perfect sensor. As a perfect sensor, whatever is in the range of field of view of the LiDAR will be notified to the system as perceived. In this way, you don't need to solve any intricate optic equation. In the advanced sensor, well, you start injecting some error model, and this error model, of course, will start taking into account that there may be some occlusion, there may be some Gaussian noise or other kind of noise, there may be some point that is statistically missed, and so on. And finally, you can dive into the physics-based sensor, in which, staying with the example of a laser beam, you want to see the propagation of the single laser beam. You want to see how this laser beam interacts with the surface of the material that hits, and you want to know how the material absorption is in that wavelength, what is the scattering, what is the forward scattering. You want to know the multiple bounces of that beam, because multiple bounces will typically create, for example, artifacts like ghosts. Finally, last but not least, because customers enjoy this as well, you can really plug the actual sensor into the simulation, and this will become, of course, an hardware-in-the-loop simulation. Here I prepare for you some images showing the rendering capabilities, and all of this can be done in real time. As you can see on the top, these tiles, they are not just texture. This is really a 3D surface in which light can bounce, and the same can do a laser beam. So all of these materials will scatter the laser energy in multiple directions. And of course, road and wetness will change definitely the reflectivity, and even creating some ghost from the camera point of view. Here you have an example in which we are coloring the points generated by a LiDAR, not according to the distance of the point from the vehicle itself, but in this case we are coloring according to the energy that is absorbed by the point that is hit. So this energy, of course, changes depending on the material that we are hitting and by the angle that the beam itself has on the surface that is hidden. So moving to the next point, we already said that well, if you want to build a 3D world in which your car can travel, you typically have a couple of chances. Or you build manually this world, and of course in this case you have the full control of the environment. You typically tend to minimize the number of objects that you inject, but this on the other hand allows you to have a very nice parameterization of the scene. On the other hand, it's very time consuming. An estimation is about 6 months to build 100 kilometers. That's a typical estimation that we have in this field. The other workflow that is possible is a workflow that is based on measurement. There are several kinds of measurements available, typically leveraging or stereo camera or LiDAR measurement. And this is typically much faster. Of course, you have a dependency on the measurement process. And of course, you can't measure everything on bad days, like with camera workflow, you can't go and measure during nighttime. and on LiDAR-based workflow, you can't go and measure on rainy days. But apart from this limitation, the workflow is pretty stable. At many of our partners is mostly automated, so can generate these 3D environments in a fraction of the time that you would otherwise need by hand. What we are actually doing, as I mentioned, is to leverage the Leica Pegasus 2. It's a lovely piece of hardware, pretty heavy, but a couple of young guys can easily manage it. Can be installed on the roof of a vehicle. And as you can see from this image, it is equipped with plenty of camera in the surrounding. This camera has a quite long focal length, so they're used to look to signals and stuff that is not exactly close to the road. For the near road, there is the 360 camera that is on top of the Pegasus. The system is then equipped with a survey-grade LiDAR. So this is a LiDAR that is in the range between 10 and 30 times more accurate than the LiDAR that a self-driving vehicle has, and is producing more than 1 million points per second. This LiDAR will give us, last but not least, not only the position of the point of the road that has been hit, but we can also record the energy that bounced back, so we can have a classification of the material that belongs to that point. So from the camera we know the color of that point, from the LiDAR we know the position in X, Y, Z, and we also have an estimation of the material properties of every single point that then will be clusterized. The system is then completed by a GNSS antenna, of course from Novatel, and an IMU, so the system is consistently on track even if you are into a tunnel. And actually the Leica Pegasus 2 is quite often used to scan tunnels. So what is the workflow? Well, as I told you, you start with this very nice piece of hardware. You can very easily scan 100 kilometers in just one day. All these measurements are directly digested by Road Factory. Road Factory has a 90% automated workflow. The 10% is missing is typically because you want to have some quality checking of whatever has been extracted. This will then write an OpenDrive file that can be validated before being used in simulation by the OpenDrive validator that we developed, and will also give you the orthophoto. So you have also a very clean, very nice top view of the scene. All this information can then be imported into the Road Designer, that is a module of Biggity. And then in the Road Designer, you can complete the description of the scene, for example, adding buildings, adding street lights, and so on. Finally, you can perform the simulation using Biggity. As an example of the scanning process, I want to give you the one of San Francisco. So the length that has been scanned is a little bit more than 220 kilometers. It took just 18 hours to go through all the roads that you can see here. The processing time is was then 40 hours, and within this 40 hours you can see the level of accuracy you can achieve from the image below. And finally, as I told you, you are mostly interested in your system under test, and this means your vehicle, the sensor, the AI driver, and so on. So this is the piece of information you want to validate through the simulation process. Great, you typically leverage an HPC center to do this, and this will create for you a ton of data. This data has then to be processed with data analytics. You need to specify which are the key indexes that you are really interested. Some of them will be referred to safety, to functionality, and to comfort of the passenger itself. And then, according to your metrics, you want to enable that the next iteration of the evaluation of your system goes and dig in the areas that are most critical for your vehicle. So this is something we are working on. We are currently developing this concept. Is at the moment a proof of concept. As you can see, it includes generation of a variety of scenario through the permutation. Essentially, you can permutate the logic of the driving participants, so how many pedestrians, what is the speed of every car, what is the position, and so on. You can permutate the static parameters of the scenario, so what is the width of the road, if the lane markings are freshly painted or worn out, and so on. And finally, you can also inject all the sort of errors of the sensor. All of these then run into an HPC cluster. Typically, thousands of parallel simulations are needed. And then all this data is pre-processed, and in this case can be analyzed via some data analytic tool. In this case, it has been used Tableau. And with this, I would say that I have concluded my presentation, and I can open the stage for questions.